Welcome all. In this video, we will be studying the instruction set of ARM Cortex-M processors. So, instruction set used by Cortex-M processor is called thumb. This thumb instruction covers both 16-bit thumb instructions and new 32-bit thumb instructions. Cortex M3 and M4 processors incorporates Thumb 2 technology. That means it allows mixture of 16-bit and 32-bit instructions for higher code density and for higher efficiency. When we talk about classic ARM processors, example for classic ARM processor is ARM 7 TDMI. The processor has two operation states. One is called 32-bit ARM state and 62-bit thumb state. So we can call it as ARM state and thumb state. In ARM state, instructions are 32-bit and the core can execute all supported instructions with high performance. This is for high performance. And in 62-bit thumb state, instructions are 16-bit, and this is basically to provide high code density or excellent code density. We will have to note that the thumb instructions do not have all the functionalities of ARM instructions, and hence more instructions are required to complete certain types of operations. To get best of both, many applications in classic ARM processor have mixture of both ARM instruction set and thumb instruction set. ARM instruction set is for high performance, thumb instruction set is for high code density. But when we observe, we have both the states in this figure. It is shown there are both the states, thumb state and arm state. And thumb state, it is 16-bit instruction, and arm state it is 32-bit instruction. In the program, if we have to move from 16-bit instruction to 32-bit instruction, this has to be done using branch instructions. So whenever branch instruction is executed, obviously there is a overhead occurring. After executing the ARM instructions in ARM state, if we have to move back to thumb state, again the written branch instruction is to be executed. There also we will have overhead. So while moving back to the thumb state, the overhead occurs. So the main drawback in this is it does not work ideally because there will be overhead in terms of execution time as well as instruction count. We will be wasting the instruction execution time as well as we are providing additional branch instruction. So it is waste in terms of both execution time as well as instruction count. And the second drawback is switching between the states, and the separation of the two states will increase the software complexity and the compilation process, and it is also difficult for the programmer to switch between the states. So with the introduction of Thumb 2 technology, the Thumb instruction set has been extended to support both 32-bit instructions as well as 16-bit instruction encoding. With Thumb 2, all processing requirements can be handled without switching between the states. So this figure shows the comparison between classic ARM processor and Cortex-M processors. As we can see, in classic ARM processor, we need switching between the state from ARM state and thumb state, whereas in Cortex-M processors, there is no switching required. All the instructions are executed with thumb instruction set, which consists of both 16-bit and 32-bit instructions. So the next thing that we will have to study before going to the instruction set is the registers available in Cortex-M processors. In Cortex M processor, we have 12 general purpose registers starting from R0 to R12. R0 to R7 is called as low registers, and R8 to R12 are called high registers. Apart from this, R13 is called the stack pointer, R14 is called the link register, and R15 is called the program counter. So the R13, that is the stack pointer, is further divided into two types. One is main stack pointer, another one is process stack pointer, abbreviated as MSP and PSP. Apart from these register bank registers, we also have special registers like try mask, fault mask, base PRI, and control register and PSR. PSR stands for Program Status Register. Program Status Register is further classified into three types, that is APSR, EPSR, and IPSR. APSR stands for Application Program Status Register. EPSR stands for Execution Program Status Register. And IPSR stands for Status Register. All the registers, the general purpose register, stack pointer, link register, program counter, and the all special registers are all 32-bit in size. So now, when we take PSR, all the bits in APSR, EPSR, IPSR is not defined. So APSR defines few bits, EPSR defines few other bits, and IPSR defines few other bits. So in the combination of APSR, EPSR, and IPSR is represented as XPSR. So this is the configuration of XPSR. In this, whatever flags, these are called as N, Z, C, V, Q, are called as flag bits. N, Z, C, V, Q bits along with GE. GE stands for greater or greater equal. Whatever is marked in pink belongs to APSR register. Whatever is marked in red, that is ICI/IT, and T, here also ICI/IT, whatever is marked in red belongs to EPSR, and whatever is marked in green belongs to IPSR. Now coming to this NZCVQ, these are called as status flags. These status flags are available in APSR register, and in general I can say it is available in XPSR register. N stands for negative. Z stands for 0. C stands for carry. V stands for overflow. And Q stands for saturate. ICI/IT. This is interrupt continuable instruction bits. So we will study this in detail later. T is thumb state, and exception number indicates which exception the processor is handling. The 3 bits, that is 19 down to 16, is greater than or equal flags for each byte lane. So this GE, ICI/IT, T, all these bits, NZCVQ, exception number, we will study in detail. Coming to status flag N. Upon execution of an instruction, if the value results in some negative value, then N flag will be set. If upon execution of an instruction, if the instruction results in a 0, Z flag is set. If the instruction results in a carry, carry flag is set. If the instruction results in overflow, overflow flag will be set. These are the 4 important status flags that we'll be using in the instructions. So as of now, we will concentrate only on NZCB. The other bits Q, ICI slash IT, T, GE exception number, we will deal later in next video. Coming to the general instruction format of ARM processor or ARM Cortex M processor, it starts with the label, followed by mnemonic, followed by operands, then finished or completed with a semicolon. Then after a semicolon, comments can be included. This label and comments field are optional. If it's required, we can use it. If it's not required, we can remove the comments as well as label. Mnemonic is also called as opcode, and it tells the CPU what operation has to be performed. This is the instruction given to the CPU. Examples for mnemonic includes move, add, sub, mul. These are all called as opcodes. Example for operand is operands tells you what are the registers or the values involved in the operation. So that is called as operands. Going on to various groups of instructions in Cortex M processors, the the complete instructions of Cortex M processor is divided into so many groups. So the first one is moving data within the processor. Next, memory access, arithmetic operations, logic operation, shift and rotate operation, conversion, bit field processing instruction, program flow control, multiply and accumulate instructions, divide instructions, memory barrier instructions, exception related instructions and other functions. Apart from this, Cortex M4 processor also supports DSP instructions. Under this, we also have SIMD, that is single instruction, multiple data operations, adding and MAC instructions, that MAC is multiply and accumulate instruction, saturation algorithm, and floating point instructions. Then coming of data that can be inserted, it is classified as byte, half word, word, or double. Byte is 8 bits, half word is 16 bits, word is 32 bits, and double is 64 bits. We will start with first type of instruction, that is moving data within the processor. Move instruction is basically used either to move a immediate value or contents of a register to another. So the syntax of move instruction is move destination register, comma, source. Source can either be a register or it can be immediate value. One important thing to note about the move instruction is move instruction is used to move at 8 bits or a byte value, not more than that. If we are trying to move more than 8 bits, then we will have to follow certain things, then we will see what has to be done. So coming to the first example, let's take move R0, R1. So what is R0? R0 is the destination register. Into R0, we are moving the contents from R1. Remember, both R0 and R1 will hold 32-bit value. So whatever 32-bit value is there in R1, that will be moved to R0. Say for example, if you have in R1 this value 0x00011005. This x represents it as hexadecimal value. If you omit giving this x, it will be taking it as decimal value. Hexadecimal equivalent of the decimal value will be stored in the register. To avoid confusions, it is always better we specify x. X indicates it is a hex value. So R1 will hold a 32-bit value. So why is it 32-bit? Each digit is 4 bits when I convert it to binary. This is a hex value. So this is 4 bits, 4 bits, 4 bits, like this 8 values I have. So 8 into 4 will give me, make it 32. So 32 bits stored in R1. That R1 content will be moved to R0. So this is a simple move instruction. So it is a register to register move. The next instruction is move S R4, R2. In previous instruction, we did not use S. Now we have addition of S. The difference is in the previous instruction, we just moved the contents of R1 to R0 and the status flags. Where are the status flags? Status flags are in APSR register, or in general, it is in XPSR register. These are the status flags. The status flags will not be updated if it is simple move instruction. When I say move S, S stands for move with status flag update R4, R2. So what is the operation that's performed? R4 will get the contents from R2, that is 32-bit value from R2 is moved to R4, as well as status flags will be updated. How will it affect? Let's take an example. R2 as 0x00000000. If I have a value of 0 stored in R2, when I move to R4, the destination register is also becoming 0. So automatically when I give move S instruction, 0 flag will be set equal to 1. It says that on execution of that particular instruction, the destination got a value of 0. Next, we have instruction called MRS. MRS stands for move to a register from special register. As I already told you, we have special registers like prime mask, fault mask, base PRI. These are all called as special registers. If we are making movements into special registers, we will have to use MRS or MSR instruction. MRS tells we are moving a value to a register from special register. So MRS destination is a general purpose register and your source is a special register. So we are moving the contents of prime mask into R0. The next instruction is MSR prime mask, R0. This tells that we are making a movement from special register into a general purpose register. So prime mask is a special register, R0 is a general purpose register. So we are moving the contents of R0 into prime mask. It is indicated by instruction MSR. So far, we studied only the instructions related to registers, that is register to register movement. Also move immediate value into R0. So to move an immediate value, we will have to use the symbol of hash. In front of the number indicates it is an immediate value. So when I say move R0, hash 0x36, 8 bits, 36 will be represented as 8 bits in binary. So 8-bit value will be moved to R0. But R0 is a 32-bit register. So when we move 36 into R0, lower bytes will become 36. All higher bytes will be appended with zeros. Remember, move instruction can be used to store only 8-bit value. We cannot use it for higher values. So this instruction, as an extension of this instruction, I can say move SR0, hash 0x00. What does this tell you? A value of 00 is moved to R0. This instruction will also update the status flag. So R0 becomes 00, as well as upon moving 0 value to R0, my 0 flag will also be set equal to 1. If the same thing would have been used with move R0, hash 0 will only move the content 0 to R0 without updating the status flags. Next, we have instruction called move W. Move W is used to move a value, 16-bit value, into lower byte of the destination register. So move W is to move to lower 16 bits of destination register. So when I say move W R6 comma hash 0x5823, immediate value of 16 bits is moved to lower 16 bits of R6 and higher 16 bits are all made zeros. And similarly, we have one more instruction called move T. Move T will move 16-bit value to higher 16 bits of the destination register. So R6, when I move 0x1234 to R6 using move T instruction, it will move 1234 to higher 16 bits and lower 16 bits will be made equal to 0. In case if I execute these two instructions together, if I execute move T after move W, the contents in R6 will be 0x1234 5823 because to lower 16 bits we would have moved 5823 because of move W instruction, to higher 16 bits of move T instruction. If you are using the instructions individually, only the corresponding 16 bits will be getting the values. If you are using both of them together, full 32 bits can be stored using move instruction. We have one more instruction called as MOVN, move negative. So when we say move n R0 comma R5, negative value of R5 or negation of R5 will be moved on to R0. Apart from these instructions, move can also be used along with certain conditions to show that. Let's start with the first one. If I give the instruction like this, move CC R0 comma R1. What does the CC means? The first C will always tell what is the type of flag and the second C will tell what is the status, whether it is clear or whether it is set. If it is C, it means it is clear. If it is C, if it is yes, it is set. So when I say move CC, that means if the carry flag is cleared, move the contents of R0 comma R1. If the previous instruction had cleared the status flag of carry, then R1 content will be moved to R0. So while executing this instruction, it will perform if condition. If carry flag is equal to 0, then R0 will get the contents of R1 or else this instruction will be omitted. Similarly, if I write move CS R0 comma R1, it will tell you to move the value of R1 to R0 only when carry flag is set. That means it will do this operation. If carry flag is equal to 1, R0 will get a value of R1 or else it will be omitted. Next few more examples. Instead of CS, I can also call it as move VS. That means if overflow flag set, move VC. If overflow flag is cleared, I can also say move equal. Move equal R0 comma hash 0. What does this tell? If R0 is equal to value of 0, 0, then the move instruction will occur or happen. Let's go to the next type or next group of instruction set, which is called as memory access instructions. This ARM Cortex M processor architecture, and RISC architecture is basically dependent on load store architecture. What is load store architecture? If you have some value in the memory, the operation, CPU operation cannot be performed on the data. First, the data or the value should be moved into the register. Only after that, CPU will perform the required operation, and after performing the operation, the value will be stored back in the register, and from the register it has to be moved back to the, will have to access the data from the memory and write back the value into the memory. So to perform the operation, we have load instruction and store instruction. Load instruction performs read operation from memory to the register, and store operation will perform write operation memory from the register. So as I already told you, we have different types of datas in ARM Cortex-M processor. It can be 8 bits, it can be 16-bit in size, it can be 32-bit in size, or it can be 64-bit in size. So based on that number of bits that we are moving, we have different categories under this memory access instructions. So the first category is 8-bit unsigned. If you are trying to move only 8-bit value from the memory onto the register, we use instruction called as LDRB, which stands for load register with a byte value. B stands for byte value. Similarly, if you are storing only 8 bits into the memory location, we have the instruction store byte. So we are moving 8 bits of value from the register into the memory location. Then this second category, 8-bit signed, the same thing. If we are moving signed 8-byte value, we will signed 8-bit value, that is 1 byte value, we will use LDR-SB, and similarly we have STRB to store signed 8-bit value or 1 byte value. There is no difference in store, it makes difference only in load instruction. Then in 16-bit unsigned, if we are storing 16-bit unsigned value from memory into the register, we use LDRH, that is word in bits. If we are storing 16 bits into the memory, then we use STRH. For 16-bit signed, we have LDR-SH. Yes, indicates signed, but we don't have any difference in store, so it is only STRH. Then if we are moving 32-bit value from register, we use LDR. If we are moving from register into, we use STR. Then if we are using multiple 32 bits, we use LDM and STR. LDM stands for multiple 32 bits. If we are moving double word, that is 60, LDRD and STRD. And for stack related operations, we have two instructions called push and pop. Push means we are, this is, if we are pushing, if we are taking out the value from the memory location, it is called as pop. So under load we classify pop, under store we classify push. It's the other way. So pop is under load and push is under store. Let us study in detail load and store operations. The general syntax for load instruction is LDR, destination, comma, source. Like move instruction, LDR also has the same syntax, comma, source. Destination is always a register and source can be immediate value. So remember, move instruction is used to move 8-bit value. If we are trying to move 32-bit value, we prefer using LDR instruction. So LDR can be used for 32-bit movement, immediate value movement into destination register, or it can be pointing to some memory location through registers. let's take one example. LDR R0 comma R1 written within square brackets. If we write LDR R0 comma R1, that means contents of R1 is moved to R0. If we write LDR within square brackets, that means contents pointed by R1. Say for example, before execution of this instruction, you assume R0 had this 32-bit value and R1 had this 32-bit value. Upon execution of this instruction, what will happen? R1 is having this value and this value is considered as a memory address. So from the memory address 0x20000000, that's pointed by R1, contents, you assume that in the memory location of this address 03 is stored, in this address 04 is stored, in this address 05 is stored, in this address 06 is stored. So the contents pointed from this memory location, which is 03, will be stored onto R0. But remember, each memory location can store 8-bit value. So registers are all 32 bits in size. So we will be accessing data from successive 4 memory location. So each memory location will hold 8 bits. So successive 4 memory locations will make 32 bit. From successive 4 memory locations, it will be stored into R0. That is from the address ending with 00 to address ending with 03 will be stored into R0. How will it be stored? It can be stored either in little endian format or big endian format. What is little endian format? In little endian format, the least significant byte will get the contents from the least significant address, from the base address. And most significant byte will be taken from the highest byte or from the most significant byte. So the memory address ending with 00 is holding 03. So 03 will be stored into least significant byte, LS. Byte will be from 01 memory location, that is 04. The next byte will be 05, that is from the memory location 02. The next byte will be 06. If it was big endian format, it is the other way around. The base address, that is from the memory location ending with 00, that is 03, will be stored in the highest byte, and then 04 in the next highest byte, and the next byte will have 05, and LS byte will get 06. So big endian is reverse to that of the little endian format. But most of the ARM processors will follow little endian. Upon execution of this instruction, R0 value will be changed, but R1 value will remain unchanged because R1 is a source register, so source value is unchanged. Similarly, going to the next instruction, store instruction has this format. This is the syntax. Store the source into the destination. Source is always a register that will be stored into destination. Destination will be a memory location. So taking an example, if we write store R0 comma R1 within square brackets, what does it mean? It is indirect way of addressing. We are storing the contents of R0 into the memory location pointed by R1. Let me assume that before execution of this instruction, my R0 had this value, R1 had this value. So upon execution of this instruction, now what is R1 within square brackets? That means it is pointing to a memory location whose address is this base address. So the contents from R0 will be stored into this base address. So 0x20000020 will get 78. This is the following little endian format. So 78 is the LS byte, lowest significant byte. So 78 will be stored in 20. The next byte, that is 56, will be stored in 21. 34 will be stored in 22, and 12 will be stored in 23. This is according to little endian format. If it is following big endian format, 12 will be stored in 20, 34 will be stored in 21, 56 will be stored in 22, and 78 will be stored in 23. It is always the reverse. One more thing we had to study in this load instruction. So I just gave you one example wherein the source was a memory pointed by a register. If we are trying to move a immediate value, you can write it like this: ldr r naught comma. In move instruction we used a symbol called as hash, but in ldr instruction we use equal to symbol, equal to 0x20 a4 1256. So this 32-bit immediate value is moved on to r naught. So now let us study some variations in this load and store instructions. We have something called as indexing in our load and store. So what is in, there are three types of indexing. One is called pre-indexing, another one is called post-indexing, and the last one is called auto-indexing. Coming to the first one, pre-indexing, we write the instruction like this: LDR R naught comma. If it is only a normal load instruction, we used to write R1 in square brackets. Here, if we have to specify some indexing, we give R1 comma hash followed by an offset value. Offset value can be positive or it can be negative. So this instruction will tell move the contents of R1 plus 4. That means if, take for example, before execution of the instruction, I will assume R0 had this value 1, 2, 3, 4, 5, 6, 7, 8. R1 had this value 0x20000000. Upon execution of this instruction, to this R1, we will be adding a value of 4. So it will become 0x20000004. From this memory location, content will be moved on to R0. Remember again, 4 successive memory locations starting with the base address of 04, that is 0405. 7 contents will be moved on to R0 based on little endian format. But remember, if we are using pre-indexing method like this, if we are mentioning offset within the brackets, the source register, that is R1, is not altered. Only the contents from the memory location is moved. But R1 still remains a 0x20000000 only. R1 content is not changed. The access is from the memory location pointed by 0x20000004, but the contents of R1 remains as the base value or the previous value itself. Only R0 will change. So that's what is shown here with an example. So if R0 had some value, R1 had some value before execution, happens to R0, we will add a value of 4. So this assume that this is the memory. From a memory location 2 followed by 7 zeros up to 3, you had a 32-bit value. This is the 32-bit value shown it together. And from memory location 04 to 07, we had this value. So upon execution, the value 0x12345678 will be stored into R1, R0, but R1 will still remain as this base address. There is no change in R1. This is called as pre-indexing. The next one is post-indexing. In post-indexing, the offset is not mentioned within the brackets, it is mentioned outside the brackets. When we write it like this, the operation that is performed is from the contents pointed by R1 register is moved into R0. The 32-bit value starting with the base address pointed by R1 is moved into R0. After moving, incremented by 4. Say for example, before execution, you assume that you had this value in R0 and this value in R1. Upon execution, after execution, R1 will become the next variation in our indexing is auto indexing. As we saw in pre-indexing, we were moving the contents from R1 plus 4 memory location into R0, but we were not updating R1 status. If we want even R1 to be updated, we use one exclamation mark along with pre-indexing, and this is called as auto-indexing. So what will auto-indexing do? Auto-indexing will update R0 with the contents from R1 plus 4 memory location, as well update R1 with R1 plus 4 value. So if we consider an example, before executing auto indexing instruction, R0 had this value. After executing, R0 will get the content from R1 plus 4, that is 20000004, that is from 04 to 07 memory location, which is 0x12345678. As well, R1 will get updated to 200000 and 04. If it was pre-indexing, this R1 would have still remained as 200000 and 00. This is the difference between pre-indexing and auto-indexing. It makes no sense if we are using exclamation mark along with post-indexing, because automatically in post-indexing, R1 is updated after execution of the instruction. Now let us consider few examples to illustrate byte loading and half word loading. So let me consider one question in this. Let us find out what is the value that will be placed in the destination register when we are trying to move 0x85 using LDRB instruction. What is LDRB instruction? Load to register a byte value. So now let me take an example. If it is LDRB R0 comma contents from R1 register, let R1 0x200000 and 00. So what are we trying to move? We are trying to move only a byte of value. A 1 byte is only 8 bits. But destination register can hold 32 bits. But we are trying to move only 1 byte, that is 8 bits. From which memory location? From memory location pointed by R1. So assume that you had a value of 0x85 in this memory location. So 0x, since it is little endian format, 0x85 will be stored in my least significant byte. 85 in binary is nothing but 1000 0101. Most significant bit is 1. So it will perform sign extension. So all ones will be filled in higher bits. So it becomes FF, FF, FF85. So whenever we are storing a byte value, there is a sign extension. Remember this. Similarly, if we are trying to store 0x30, what is 30? 01, 0011, 0000. Most significant bit is 0. So when you are trying to store 0x30 into R0, it will be stored as R0 equal to 000000 and 30. So the sign extended bits will be stored in most significant bits. So let's take one more example. LDRB in brackets R1, R2, N hash 2. This LSL tells you will be performing left shift, and this hash 2 tells by how many bits. So this instruction is telling perform left shift by 2 bits, the contents in R2, then add it with R1 and then move it to R0. So this instruction can be written like this. R1 plus R2 left shifted by 2 bits. The contents 8-bit value from this memory location is moved on to R0. Why only 8 bits? Because it is LDRB instruction. LDRB will move only 8 bits or 1 byte value. Let us take one example. Assume that in R0 you had 0x20100101. In R1 you had 0x00000001. In R2 you had 0x00000001. Now, what is the operation that is to be performed? R2 is first left shifted by 2 bits. So upon left shifting, this is one first left shift, this is second left shift. So R2 will become 0x00000100. This one bit comes to this position because we are performing left shift by 2 bits. So then R1 content, which is nothing but this one, is added with R2. So upon addition, we get 00 is 0, 10 is 1, 0000 x 0. From the memory location pointed by this address, this is the address. We have calculated the address now. This is the address. You assume in the memory, this is the address, and this is the memory address 0x00000101, which we are interested in. In that we had a value of 01. Since it is LDRB instruction, only 8 bits, that is 01, is moved on to least significant byte, and the rest of it is sign extended by zeros. Remember, only 0 to 3 bits shift is allowed. I cannot write hash 9 or hash 10. It is not allowed. Only 0 to 3 bits shift are allowed. Now, if R2 was 0x 00000111, what will happen when you perform left shift? All the bits are shifted left by 1 bit. So this is shifted here, this is shifted here, this is shifted here, and so uh, one mistake we have made. I will rectify that mistake. See, when I do 2 bits shift, just a minute, I will erase this and rewrite it. So when I perform this operation, what is there in R2? This is an hexadecimal value. R2 will actually be, let us write 32 bits value, 0000, 0000. This is for this. Similarly, you have 8 bits for this. You have 8 bits for this. When I represent 01, I have 0000, 0001. When I perform shift, it will become 0000, 0100. So this should have been 0. This is proper. So I had shown it like this. So instead of showing, I'm showing it to you separately so that you will not get confused. So now it will become this one. What is this? This is 4 and this is 0. So this will be 00 and 04. So what is the address? It will become 0 and 5. So let's assume this is the value from 05. The value was 03. So 03 will be stored into R0. Similarly, one more example we had taken. We had assumed let R2 be 0x000010. If it is something like this, if it is 1, 1. So now let us write it in binary. So this is all zeros. This is 8 bits, 8 bits, and 8 bits, 8 zeros, 8 zeros for this. And this 1 0 is nothing but 0001, 0000. And this 1 1 is nothing but 0001 and 0001. When I perform 2 bits left shift, it will become, all these will remain as it is. This is 1 0, this is 1. This will become 0100, which is nothing but 4. So 1014, 0000. From this value, it will be moved. So this is how LSL will work. If we are using, we will take one more example. If we give the instruction like this, LDRD, what does it mean? We are moving 64 bits from a source register or from the source location into a register. But all the registers available in ARM Cortex M3 and M4 are all 32 bits inside. So we need two registers. So we will have to specify R3, R4, contents of R0. So 64-bit value pointed by the base address R0. Base address R0 can store only 8 bits. So like this, how many memory location? 8. I need 64. So 8 into 8. From 8 successive memory locations, it will be stored into R3 and R4. Both R3 and R4 are destination registers. So in this video, we have studied two categories. One is moving instructions between the registers, and we have studied memory access instructions. In next video, we will study the next categories of the instruction set. Thank you.